Yeah, I have prepared two presentations for this afternoon. One is more general about structural health monitoring, how to design it, what are the benefits, how to evaluate if for a given application or structure it is beneficial to use it. And then there will be a second one which is more technical about fiber optic sensing, where I will present several applications of fiber optic sensing technology to the monitoring of structures. Can I? Yeah. Okay. So first, the first presentation is about structural health monitoring, benefits and applications for infrastructure management. What the first question I'd like to ask is, what is structural health monitoring and why you would like to do it? I think when I ask all of you, should we monitor the health of structures, everybody would say yes. But how and why, I think everybody will give a different answer. So there might be reasons for monitoring bridges, but for what reason? Why are we monitoring bridges? Just putting sensors on them, is it monitoring or is it just installing sensors? Are we talking about safety? So we heard in other presentation that maybe there are hidden defects in structures. So monitoring them might reduce the uncertainty and increase the safety of structures, for example, in the case of a dam. So that could be one reason for structural health monitoring. Maybe other people that are involved more in the construction phase are thinking about risks during construction. So try to minimize risk associated maybe with neighboring structure. So this would be a very different goal for using maybe the same sensors, but for a very different application. In the case of a pipeline, structural health monitoring might be for protecting the environment. We want to avoid spilling oil into the environment. And in this case, the main reason might be environmental risk associated with that. Maybe there are other applications where you want to showcase new technologies, so want to be a leading edge building, for example. So installing modern infrastructure, including structural health monitoring, can be perceived as a way to increase the prestige of a building, for example. Preserving natural resources. For example, if we want to extend the lifetime of a structure, instead of replacing it, it's also a way into sustainable economy and preserving natural resources. Maybe there are managers in the room that are more interested in having more reliable data about the condition of a structure for managing purpose, so for maintenance, for deciding what to do in the future with the structure. So in this case, the same network of sensor can have, again, a different purpose. So the presentation is really talking about all of this and see how those different benefits can be applied, but also to make sure that when you design a structural health monitoring system, you have the final goal or goals clearly in mind, so that the design of the monitoring system becomes optimal and you achieve your intentions. So maybe when I started in this field about 20, 25 years ago, this was a kind of research topic. So people were thinking about it in universities, especially for structures like bridges. Maybe it was more common practice in dams or nuclear power plants, but for bridges and buildings, it was really a research topic. But now it has really become an industry. So how has that transition happened? How those companies are addressing these industrial needs? So the goal of the presentation, when we move from research to an industry, the main change is that an industry is based on cost and benefit. So you want to make sure that what you offer as a benefit, so that you can justify the cost of offering that solution. So when we talk at cost-benefit analysis, we need to understand what are the costs and what are the benefits. So I will try to give you a little bit of insight about these two parts of the equation in the next few slides. So when you define the cost of a structural monitoring system, it's mainly divided in two parts. There's an initial capital investment that includes hardware, installation, etc. But there are also operational costs that are associated with using the structural monitoring system. So it's very important to consider those two aspects when defining the cost of such a system. So in terms of capital investment, there are design costs. For example, understanding how the structural monitoring will integrate with the structure itself, especially for a new structure, how you install it, when you install it during the construction phase. There's the planning and project management part. So these are more engineering services, let's say, associated with structural monitoring. Then we have the hardware cost for buying sensors, cables, or no cables if it's wireless, but data acquisition and management hardware, and the communication. So very often people concentrate a lot on those costs, but these are only a part of the whole cost of ownership of a SHM system. Then you have the installation cost. Can be quite different if it's an existing structure or a new one. In particular, when you are building a new structure, you need to make sure that the installation of the monitoring system is compatible with the schedule of the construction site itself. Then you have configuration, commissioning, and reporting. And finally, it's quite important to consider the operational costs, including system maintenance, spare parts, energy, and communication cost. But also, more importantly, make sure that you have you take into account the costs associated with using the data. Data management, data publishing, data archiving, how to make sure that the system is maintained, but at the same time provides useful data to the owner. So that's how you define the total cost of a structural health monitoring system. And I really encourage you to consider it as a whole rather than concentrating maybe on the cost of individual sensors. That's against maybe my interest as a supplier of hardware, but I prefer that maybe you spend a little less on sensors and data acquisition unit and set aside a little money to do something useful with the data once it gets generated. Because I've seen many projects that were very successful from my point of view. So the system was installed, works, and provide data, but then that data doesn't get used. So that's a pity, and I think in the end, it's a problem for the industry. If people invest money and don't get a benefit in return, in the long term, it's not good for structural health monitoring. Data analysis, interpretation, and reporting, that's important. We will see in some cases might be trivial to analyze the data. If you're looking for a movement and you measure the movement directly, maybe it's very easy to analyze. In other cases, there might be a need for more sophisticated data analysis and interpretation to go from the raw data to an information that the owner can use to make decisions. Okay, so if I measure strain, and I report the strain evolution, that's not very useful for the owner of the structure. He wants to know what's the residual fatigue life, for example, or if that value is in line with expectations or not. So data analysis and interpretation is where the value of structural monitoring really becomes apparent. If you want to get numbers that can vary a lot depending on the type of structure and also the level of risk associated with the structure. But typically, we're talking about 0.5% to 3% of the construction cost. And the cost of the hardware, so the cost of buying components, is typically only half of the total cost of ownership. So the rest is services, engineering, installation, and data analysis. Okay, so now that I have scared you with the cost, let's look at the benefits. Why are we willing to invest this 1 or 2 or 3%? Might seem a little amount, but compared to the cost of the structure can be a significant investment. So the owners, rightfully so, want to understand what are the benefits of structural health monitoring. I try to separate it between hard benefits and soft benefits. So the hard benefits are those that you can quantify in euros. And the soft benefits are other benefits that maybe are less or evident or less simple to quantify in terms of monetary return. Okay, capital value is not really a benefit, so adding something to a structure adds to its value, but by itself is not very useful. So the first tangible asset is the reduction of risk or peace of mind, if you want to call it that way. So that's both a hard benefit and a soft benefit. The real monetary benefit is that risk can be associated with a monetary value. For example, insurance costs are related to how well you can quantify and control your risks. But it's also a soft benefit because it can be sold to the community, for example, to make sure that the pipeline, for example, or a dam is not dangerous. Here's an example from a close-by project. This is a tunnel here in Barcelona, where the owner wanted to make sure that there was no crack in the tunnel vault. So they installed a distributed monitoring system to monitor that tunnel. The cost was very high for that instrumentation. And this includes everything, including installation, hardware. That's really the total cost. But there was a significant reduction of risk. And so the benefit was quite immediate in terms of reduction of insurance cost for the project. Here's an example of how that might be done. And in the second presentation, I will go into more detail about how this works. But the idea was to cover the whole length of the tunnel with sensors so that no matter where a problem or a crack might appear, there will always be a distributed sensor picking up that particular location and issuing an alert. So this was really a detection system rather than a structural monitoring system, designed to detect a very particular event that was expected or was feared on that structure. Increasing safety, again, a hard and soft benefit. This is related to cases where the risk are, let's say, very low probability but high consequences, like a collapse or something that is unlikely but at the same time very detrimental or very dangerous. So for example, we have instrumented an area that is prone to sinkholes. So you see this huge sinkhole that has basically taken away one of the train lines. In this case, an event like this one, it's obviously very dangerous. And if you can detect it early on and you can stop the traffic, then you can have an immediate benefit in terms of safety and security. In this case, for monitoring about 6 kilometers of of train line, the total cost was in the order of $400,000. And again, the benefit associated with it was related to the insurance cost and the safety of the rail operation. Here you see a couple of pictures of installing the distributed sensing cable in the ground. And when the ground starts to move due to the sinkhole, then we can pick up and display on a map where that event is located. So here, for example, you see the cable is running along this railway line here. Here we have a highway, and there's another cable running along that one. And here is a residential area, so there's also a cable going around that. And you can see a couple of sinkholes that have formed in the past. So you can imagine if something of this size would happen a few meters away. That's, by the way, that's the location where the other picture was taken. It really damaged the railway line. And everything gets measured from a central location here. So here's an example where the cost was relatively high, but it's associated with a very high risk as well. So it is justified from that point of view. Increase of quality. Quality is, again, hard and a soft benefit at the same time. Quality often is related to controlling and measurement. So there are some theories that show that when you control a process, you tend to increase the quality. Even though you don't do much maybe with the data, you can imagine that contractors, for example, will maybe unconsciously produce a higher quality building when they know that someone is checking or measuring what they're doing. We're getting close to Christmas, so I know that works for my kids. When I tell them Santa Claus is watching you, they behave much better, even though they have no direct feedback that that observation really happens. Knowing that maybe he's looking helps improve the quality of their behavior. So that it's quite human and works also for buildings. Here we are maybe at the other end of the spectrum. It's a project we've been running for almost 20 years now in Singapore, where every new building that is built by the housing authority gets an instrumentation that costs about $25,000. So it's pretty small investment compared to the cost of the building. And now we have instrumented almost 1,000 buildings. So it's very large project. And the goal for the housing department was to improve the quality and make sure it's constant across buildings. They are designed to be the same, but they noticed that depending on who the contractor was, the quality was varying. And in this case, they are also aiming to an image change, so that when they sell the buildings, they put forward the structural health monitoring as one of the features of the building itself. So it's perceived as an additional value for the owners. In particular, they use it to check during construction, but also later on, if there is a typhoon or there is an earthquake, they can check that the building has not been damaged by that event. Here are a couple of pictures of how you install the sensors in the columns of those buildings. They are then connected to a surface box where the readings can be taken. This is a picture of how manual reading might be taken. Some of the buildings have manual reading, others have automated readouts. And here's an example of the evolution of strain in the columns over, in this case, about 6 years. But there, as I said, we have buildings that are getting close to 20 years. You see the initial construction phase with shrinkage of concrete, and then after a few years, you get very stable readings. You can see here, for example, some settlements of columns that have induced some strain, but others are very, very, very stable. So after an earthquake, I think there was one earthquake here, when they did a little, some additional measurements, you can tell that there is no change before and after the earthquake. So that's a good indication that the building didn't suffer any degradation. This is an interesting aspect. I think in many of the presentation we've seen, structural monitoring is presented as a way to address risks. But in my experience, I found that there are also applications where you can find the opposite of a risk. I would say that you find benefits that are hidden in the structure that you didn't know. So, for example, we had several cases of structure that didn't, bridges in particular, that didn't look very good in terms of visual inspection. But once they were instrumented and when the recorded performance was compared with the calculation and the model were updated, they found out that the structure was in much better condition than that it was expected. In particular, because the quality of material was better than assumed. And also there were some effects like rigidity in connections, etc., that were not really taken into account during the calculation. And so I will show you a couple of examples later on where it was safe to extend the lifetime of the structure without any major refurbishment or replacement of the structure. So I think that when we talk about structural health monitoring, we shouldn't only be afraid of hidden defects, but I think the main goal is to reduce uncertainty. But the uncertainty can go in both directions. Sometimes they're better than you think, and in other cases they're worse. But you want to know. That's why we measure something. So here's a very nice example where there was a kind of immediate monetary benefit. It's an arena, ice hockey arena in Canada, in Halifax. And that arena is also used for concerts. And of course, it's used for concert in winter, where you cannot do them outside, for obvious reason that you see from the picture. And a few years ago, Canada updated their codes about snow load, and they increased the load that must be taken into account on roofs. And when they recalculated the load-bearing capacity of this roof, they found out that it would be very difficult to hang any equipment from the roof for the concerts. So that was a major problem, because when you do the concerts, you want to use the roof also for hanging equipment. And so there was a plan for refurbishing or even replacing the roof, but that was very expensive. And then one structural engineer said, well, I think that roof might have some reserve capacity because of the connections are stiffer than we calculate. But to prove it, I want to install a structural health monitoring system. So in this case, the total cost of the project was in the order of $250,000, including modeling the roof, installing the sensor, taking readings, and analyzing the data and proving that the structure was in better condition than expected. So here's a picture from the inside. You see during the hockey game, there are these things hanging from the roof, but during concerts, there are even more equipment used in there. So here's an example of a rock concert, and you see all the lights and scenic equipment. They are also attached to the roof itself. So to address that, we have installed a network of fiber optic sensors that measure strain on some members that were selected as the most critical from the finite element analysis, and also a total station that would measure the deflections of the roof, so that we could correlate the strain with the deflection and with the snow load or concert load on the we are probably the only one that have ever used a rock concert for a load test on a structure. So that was really the worst case scenario. You have the fire inside and the snow on the roof. And here you can see the evolution of strain. So in this particular case, we have the Ozzy Osbourne concert, and at the same time we have a snow and freezing rain. And then the evolution of strain was compared with the limit state that was about 800, so it doesn't even show on this graph. So in the end, the engineer was able to prove that the roof was able to sustain a combined snow and load effect. So in this case, the payback was kind of immediate. So I think the project for strengthening the roof was 2 or 3 million, and with 250,000, they achieved the same, basically the same goal, without compromising the safety of the structure. Another benefit is early detection of defects. That applies in particular to new constructions, where you might want to discover problems as early as possible, maybe before they become visible to a visual inspection, maybe while the guarantee period of a new structure is still active, so you can ask the contractor to repair the structure, and also to make sure that if it gets discovered during the construction, you already have all the equipment on site to fix some issues that might become much more difficult or expensive to fix once the structure is in service. Here's an example of a bridge in Switzerland that was enlarged and refurbished about 20 years ago now. And so the owner wanted to make sure that this strengthening was really effective. So he wanted to compare the deformation in the newly added concrete with the existing concrete to verify the hypothesis that the two were working as a wall. In this case, the approximate cost was about 150,000 euros, and the benefit was to verify the design and that there was no defect from this application, so that the bridge would have a good lifetime starting from this refurbishment phase. For example, here we see some early age deformation that we monitored, and we were able to detect some cracks that were appearing in concrete when the concrete was still inside the formwork. So this was used to optimize the concrete formulation, and in a later stage that you see, let's say they optimized the concrete to make sure that those effects wouldn't appear. Also, we have installed some sensor in the old concrete and in the new concrete, but close to each other. And as you can see on the bottom picture, they show a very similar behavior. So that's a good indication that the two concretes, the old concrete and the new concrete, are behaving in the same way. So again, peace of mind, confirming the design hypothesis. And this, I would say, is a very common goal for owners, to make sure that the structure is really behaving as expected, or that nothing is happening. That's also very useful information to get from a monitoring system. If we look at the other extreme of the life of a structure, towards the end, towards the, let's say, third age of structures, we see that, in particular in Europe and North America, many structures are reaching the end of their original design lifetime. But in reality, there is no end of life for structures. When people design a bridge, they say, oh, it has a 50-year or 70-year or 100-year lifetime. But one day that 100-year comes and nobody says, okay, let's close the bridge, and it's dead. Bye-bye. there's more and more need to safely extend the lifetime of those structures. So in this case, we can do a little simplified exercise and look at what could be the benefit of monitoring and updating of hypotheses through structural health monitoring. So let's imagine you have a number of bridges that are candidates for replacement. They're old, they're apparently in bad condition, so you decide that in the following 5 years you're going to replace those buildings. So let's first assume that simply replacing the buildings will cost 100 millions, for example. So that would be the cost if you simply go ahead and replace the structure itself. Now you can assume that instead you do something different. You first install a structural health monitoring system, and then you use the data obtained from that monitoring system to assess the real condition of the bridge. And if they're found in good condition, you can extend the lifetime. And if you find they're really bad, you still need to replace them. So we assume that the cost of doing that is 3% of the reconstruction cost. And we assume that out of your 10 bridges, 2 of them are found to be okay. So they can still be used, maybe continuing the monitoring, but they don't need immediate replacement. And I would say this is a pretty conservative figure. In my experience, I've seen that maybe half of the bridge are in better condition than expected when you do in-depth monitoring. Let's also assume that maybe another 20% of the bridges are in bad condition, but might just need some update or fixing, and they can be saved with investing about 30% of the cost of reconstruction. So instead of spending 100 to replace them, you spend 30 to fix them. And the other 60% of the bridges, they are really bad and they need to be replaced. So for those ones, basically you wasted your money in doing the re-engineering and monitoring, etc. But when you calculate the cost of that strategy, you find that the cost is the 3% for structural monitoring, plus the 20% of the bridges that need 30% of the cost, plus the remaining bridges that have full cost. So in the end, the cost of that strategy is 69% compared to 100% for a total replacement. This doesn't take into account the fact that with this strategy you end up with 10 new bridges, and in this case you only have 6. So you would need to consider also the difference in capital value and the fact that those bridges maybe in 10 years or 20 years will still need to be replaced. But a strategy like this one can really be beneficial to optimize the decision on structures reaching the end of the lifetime. I think it's very important that when decisions like this are taken, more quantitative information is taken into account. Not only visual inspection, maybe not destructive testing, but more information closer to the structure, behavior, and condition of the structure. An example of lifetime extension is this bridge in Sweden, is the Göta Bridge. It's a bridge that was built in the 30s and has had problems of fatigue cracking in the steel girders. It's going to be replaced in 2020, so we're about 4 years away from having the new bridge. But the owner wanted to keep it open, and it's a very important link for the city of Göteborg. And so we were asked to design a monitoring system that would detect cracks that might appear on the bridge itself. That's quite challenging question because you have no idea where the cracks might appear along the 1 kilometer long bridge. So what we did was to install a distributed fiber optic monitoring system, and that was very expensive. It's about €1 million project. But it allowed the postponement of the replacement of the bridge for about 15 years. So that system was installed almost 10 years ago, still in service. And we're going to use it for 4 more years until the new bridge comes into service. Here you see how we approach this problem. The cracks are typically appearing on the lower flange of the beams. So we install these distributed fiber optic sensors, and when a crack appears, they pick up a peak of strain, and they can then localize and alert the owner about the onset of this crack. So the beauty of this system is that it sends everywhere. So it doesn't measure very accurately the crack opening, but as soon as you have a crack, it will tell you have a crack on beam number 3 at location 354. So you can send an inspector and verify and decide what to do about it. And actually, during these years, we have indeed detected a couple of cracks, also some issues related with corrosion. So it has been a successful way to safely extend the lifetime of this particular bridge. Final benefit of structural monitoring is the increase of knowledge. That's maybe more related to research or, let's say, universities, but also owners that have a better understanding of how the structure behave and age. So, for example, this was a project we did in the United States, monitoring a shaft for deformations, simulating earthquakes, and understanding how that behaves under earthquake loads. Can I have some water, please? Yes. In this case, the total cost of instrumentation, but the test itself was about $200,000. In this case, the benefit is more research-related, so grants, publication, etc. But it's quite common to use structural monitoring system as a monitoring tool. There's also more and more structure that require structural monitoring as part of regulation or standards. For example, nuclear power plants or dams have mandatory structural health monitoring systems. And so in this case, you need to install it to cope with the existing regulation. Examples, again, nuclear power plants. Here's a project in Finland. Is EPR new generation nuclear power plant, and the instrumentation is massive. There's really a lot of instrumentation in those nuclear power plants. Basically, most of it is driven by regulation, so it's mandatory monitoring. So it might be that other type of structures will have mandatory instrumentation in the future. Finally, we have seen cases where monitoring was more of a marketing tool. So the owner wants to present the structure as innovative, as high quality, as leading edge. So installing a monitoring system is part of that strategy. Thank you. So you might have wondered what that bridge is. You've seen it for the last couple of days. Is the reconstruction of the I-35 West Bridge in Minneapolis. Is the bridge that fell down about 6 or 7 years ago. And we were part of the reconstruction project where we instrumented the bridge, the newly built bridge. The main reason for the monitoring in this case was to reassure the public. Basically, the community in Minneapolis was quite shocked by the fact that the bridge fell down and took the life of several tens of people. And so they wanted to make sure that the new bridge was perceived as safe, so that people would actually drive on it. That was the number one goal, I would say. At the same time, the monitoring was also helping the fast construction schedule. The bridge was built in 1 year, from collapse to reopening of the bridge. So it was a quite interesting project from the point of view of scheduling, installing, monitoring system, etc. And we were using some of the sensors to help the fast construction pace, for example, analyzing how quickly the concrete was hardening so that they could cast the next phase, etc. There's also a plan for long-term structural health monitoring, and in this case is the local university that is using the data to monitor the bridge in the long term. We installed a number of sensors, both traditional and fiber optics, to monitor deformation in the piles, in the foundation of the bridge, in the columns, and in the deck. We have strain gauges, temperature sensor. We have linear sensor to monitor the expansion joints. We have accelerometers in the main span to measure the vibration of the bridge. We have corrosion sensor to measure the penetration of chlorine into the deck from de-icing soles. And we have fiber optic sensors to monitor the deformation of the main span. So on the bottom, you see a few pictures of vibrating wire, corrosion, fiber optic, and data acquisition unit. In total, about 300 sensors were installed on this particular bridge. And on the two sides, you can see an impression of the final aspect of the bridge itself. Here's a load test on the bridge. With some example of results. The peaks are the different load cases. So the fiber optic in this case was also used to compare the recorded strain with the calculated strain to make sure that the bridge was matching the calculation. And as in many, many cases, we found that the strains were much lower than expected. So there's some additional stiffness in the bridge compared to the calculation. Now, in the final part of this presentation, I would like to walk you through a method that we have developed to make sure that when you design a structural monitoring system, you do something useful that maximizes the owner benefit compared to the cost that is investing in the system itself. It is based on 7 steps that we try to follow in our projects. And I will go into more detail about each of these steps. But first of all is identification of the structure. Then step number 2 is acquire information on risk and opportunities, working together with the design engineer and the owner. Number 3, establishing expected responses to those risks and opportunities. Number 4, designing the structural monitoring system and select the appropriate sensors. Number 5, install and calibrate the system. Number 6, acquire and manage data. And number 7, assess the field data. So let's have a look at each of these steps in a little more detail. Identifying structures. I think you have established a list of candidates for structural monitoring. I imagine that it's quite overlapping with what I have here. We've seen that the main benefit are really achieved in this type of structures. So first, new structures that have some innovative aspects. For example, use of new materials, use of new construction techniques, etc. So in this case, there might be uncertainties related to these innovative aspects. The second class of structure that can benefit from SHM is new structures with unusual risks and uncertainties. For example, geological or geotechnical conditions elevated seismic risk, meteorological risk, for example, typhoon, etc. Aggressive environment, for example, concrete structure in close to the sea, or maybe in the Alps where you have de-icing, etc. Maybe vulnerability during construction. Maybe there are some construction phases where the structure doesn't have the final shape and is more vulnerable to earthquakes, for example. Or maybe when building in countries where the quality of materials and workmanship is not certain. Also structures that are critical at a network level, for example, a bridge that is difficult to replace, or in an area where closing down a bridge might create a very long detour. In this case, maybe the bridge itself is nothing special, but it's very important at the network level. There are also what I would call monitoring by representation or example. For a typical example are overpasses. Maybe in your network you have several overpasses that are almost identical or very similar design. So by monitoring one or two of these, you can gain insight about the behavior of all the others. We have already discussed about the last two, so existing structures with known deficiencies or very low rating and candidates for replacement or major refurbishment work. So if you look at this, you can kind of distinguish two classes of structures that we see beneficial. One are those in the infancy, so new structures during construction, early age, etc. And then these ones are more the structures towards the end of the life. So we see that these are the two parts of the lifetime of a structure where monitoring is more beneficial. The part in between, I would say, is also useful in many cases, maybe to prevent getting into this low rating or deficiency area. But if you don't have information from the beginning, it might be more difficult to prove the cost effectiveness of a monitoring system for the mid-of-life type of structures. So once you have decided that a particular bridge or tunnel is a good candidate for SHM, the next step is to design a monitoring system for it. And you do that through a risk analysis. And I tend to call it a risk opportunity analysis because, as I said before, sometimes there are negative surprises, but there can also be good surprises. So you find some residual capacity that you didn't assume, and that's an opportunity, an example of opportunity. So when you do this risk analysis, you get a list of possible events and degradation that can affect the structure, their impact, and their probability. So the result is a list of risk and opportunity that must be addressed by monitoring or by inspection. For example, you might identify loss of pre-stress or corrosion or settlements or earthquake, and you can list those risks and prioritize them according to their impact and probability of occurring. Once you have that in mind, you need to understand how this risk would become apparent. So how do you measure or observe the onset of that risk? Some cases are very direct. For example, if you're afraid of a crack appearing, then you can observe the crack directly, maybe. But in other cases, it might be indirect. For example, if you have a settlement or if you have corrosion, maybe you have to look at something else to identify that the onset of that particular risk. At this time, you can also quantify the expected responses. So that's important to choose the appropriate measurement system. You want to know if for example, if you're expecting a tilt resulting from a settlement, you need to know more or less the order of magnitude of that tilt to select the appropriate sensor. And maybe you can define where to place the sensor or where these responses will appear. And at this time, it's also where you decide which risks are better addressed by regular inspection and which one are better addressed by structural monitoring. So I think the two are very complementary. There are some things that are much easier to detect by visual inspection. You would need thousands of sensors to do the same job that an inspector can do every 3 or 4 years. And there are other things that are almost impossible to observe for an inspector, so they are good candidates for structural monitoring. Or maybe you need more frequent acquisition than what you can do with inspection. So this brings us to point number 4, is the design of structural monitoring system. And I'd like to point out this is only step number 4. I've seen cases where this is step number 1. Someone say, oh, I want to monitor a bridge. Let's put a list of sensors. But if you don't do the analysis before, you might install something that works perfectly, but it's not useful. So the idea here is to design something that really answers to a question. I always tell to my customer, before you install a sensor, you need a question to answer. If there's no question, you don't need any sensor or monitoring system. But assuming we have identified legitimate question to answer, then you can select the appropriate sensor, consider the lifetime of the system. Maybe the system is only useful during construction, so the lifetime is not so important. In other cases, like we supply piezometers that go in the foundation of dams, they must be very durable because they cannot be replaced in the long term. This is also where the budget comes into play. And again, it's very useful to have a ranked risk list because you can start at the top, and when the money finishes, then you will need to accept the risk that fall behind or below that line. Reliability and redundancy, also an important consideration, and installation and schedule. So is it possible to install the sensors during construction? We've seen this morning examples of using wireless technology that enables you to install sensors in early phase of construction. That would be a good example of taking into account the construction schedule and sequence when considering the design of a SHM system. Installation and calibration, that's more operational. Data acquisition and management, quite important to make sure that the data is preserved for the long term. So it's well documented, it's saved in a way that can be understood for many years. Ideally, it should be self-explaining, so that if someone finds that data in 20 years from now, they can still make sense of what you measure today. So that's very important. I think speaking with some of you today and yesterday, they said, oh, some of our bridges that we have today, the drawings are very old and don't correspond to reality, etc. So let's make sure that people in 20 years don't tell the same about what we're doing today. And also for structural monitoring, if we acquire data, for example, during construction, it's very important that we preserve that information in a way that will be useful for the next generation of engineers, maybe inheriting the structure down the road. And step number 7, of course, is the most important one. That's where you get the value from what you have installed. By analyzing the response of the structure, the engineer can identify if the risk and degradation have materialized or if the opportunities are confirmed. So this is where the benefit of doing the other 6 steps really comes into life. If you have identified your risk correctly and you already know how they will become visible, then when you measure something, you can usually tell why you're measuring that change, for example. And you can guess, okay, I'm measuring a tilt, and I was expecting a tilt if I had a settlement, for example. So probably there's a settlement going on. So the risk assessment also helps in the data assessment to make sure that when you measure something, you know why and what is the probable cause of that result. Establishing procedure to respond to detection, that's very important. I always tell people never set a threshold or an alert if you don't have a clear plan of what to do when that alert goes off. Because one day it will go off, and you need to make sure that you know what to do about it. It can be close down the bridge immediately, or it can be write a report in the next 2 years. So these are two very justified outcomes of measuring something out of range. So everybody needs to be clear what happens if we exceed a certain threshold. And the monitoring is, of course, a kind of interactive process. So you might discover something unexpected that will trigger additional inspection, testing, or maybe even installation of additional sensors. And finally, the result of monitoring is typically becomes visible in terms of alerts, warnings, and periodic reports in a format that must be useful for the owner and the engineer. So also the format of the report must be agreed so that we don't supply data that is not useful or presented in a way that is not understandable for the people that can have some benefit from the monitoring system. So I'd like to conclude this presentation by talking a little bit about the retaining forces. Why we don't have more structures with structural monitoring system installed. What is retaining this technology from being used more widely? Some common problem is the difficulty to estimate cost and benefit, and I hope this presentation helps a little bit in that direction. But I think it's very important to address those questions, and we need to prove that the investment is really worth the money that is put into a structural health monitoring system. There has been cases also where the owners are scared by the quantity of actors that need to be involved to install a monitoring system. There's the supplier, the engineer, someone installing it, someone maintaining it, someone else maybe analyzing the data. So we try to simplify that by combining professionals to work together and make sure that the system is installed and managed properly. Also, there's often a lack of resources to manage the projects. It's time-consuming to fully get the benefit from structural monitoring. It's very important that someone is keeping the system alive and analyzes the data and does something about it. So it's important to have some resources, internal or external, dedicated to using the monitoring system. Also, there's been a lot of examples of monitoring system that didn't produce useful information, but only data. That's a danger, that you end up with a lot of numbers, but no useful information. And of course, limited budget are always a limitation to applying this. Retaining force number one is doing nothing. That's a very difficult, let's say, competitor for my company, for example, because it's very cheap. Doing nothing can't beat the price of that guy. So that's really sometimes an obstacle that must be that you must pass across. And to do that, of course, we need to demonstrate that doing nothing is more expensive or more risky than doing something reasonable on the structure. Another problem is that monitoring and increasing safety is not always very sexy politically. Politicians prefer to fix potholes and remove the snow from the roads because that's very apparent to the users and the people. Installing a network of sensors to improve the maintenance of structure, maybe is less interesting an investment. So that's number one. Number two, retaining force. And number three, of course, is keep doing what you always did. So that's probably a good plan in most cases, because I wouldn't say that we're doing a bad job of managing structures. So keep doing what you always did right. I think it's a good plan, but sometimes you need also to consider some improvements to the current practices in managing structures. Okay, so where is the universal recipe for developing structural health monitoring? I think it's understanding the user needs and identifying the benefits is crucial. So it shouldn't be just a technology that we try to push, but it's important to identify why is that useful for the owner. And as I try to say, that the good structural health monitoring designers has 2 years, but only 1 month. So we need to listen and to design and implement a structural strategy, structural monitoring strategy. We can only do that in cooperation with the designer and the owner of the structure itself. So that's all I have for this presentation. And
thank you very much.
If you have any question.
Any question?
Okay. Thank you very much indeed. Very clear and heartening presentation, actually. To say that structural health monitoring should answer a question is fundamental. Of course it is. And I know you know the answer to this question, but it could be seen that there's a loop in the use of a structure to calibrate the monitoring system, and then using the monitoring system to calibrate the structural model. Mm-hmm. Could you explain that?
Yeah, that's an interesting question and approach. And we've seen more and more of that being applied, so that during the lifetime of a structure, you kind of update the model of the structure itself. And that's change of mind that sometimes is difficult for the engineer, because I've seen examples of engineers that are asked to recalculate an existing bridge, for example. And they pretty much do in the same process that they do to design a new bridge. They model it, they assume something and make a calculation. But when we talk to them, we say, look, there's a difference between designing a bridge that doesn't exist and a bridge that is there. Because if the bridge is there, you can observe it. So some of the uncertainties can go away. So if you are designing a new bridge, you don't know what the concrete might end up in terms of quality or what type of settlements you will have, etc. But once you have the structure, you can measure it and reduce your uncertainty by measuring it. So a way of improving your model is to reduce some of the uncertainty, and maybe you can be less conservative on some of the assumption, or maybe on the other end, it turns out that some of the things you assumed are worse than reality, so you can update your model accordingly. But keep in mind that it's different when you redesign something that is existing, because you have a chance of going out and looking at the structure. And maybe in some cases, the structural engineers have been somehow removed from the physical reality of construction. So they tend to work on models, and then it's passed to someone else who physically creates the structure. And the feedback that existed many years ago of observing the result has somehow been lost. And maybe we can bring it back through structural health monitoring.
Otra pregunta.
Hola, buenas tardes. En primer lugar, agradecer por la exposición que has hecho y preguntar sobre los sensores de corrosión del acero a los que has hecho referencia. Si sirve, como en esta viñeta que hemos tenido al final de la persona que está picando, en estructura metálica, o también sirven sobre armadura de hormigón.
Sí.
¿Cómo funciona y qué es lo que mide fundamentalmente? Si es intensidad de corrosión, si son índice de cloruros ambientales o...
Yes, so the corrosion sensor that we have installed, for example, in that bridge can sense the penetration of chlorine and can sense the potential of corrosion at different depths in the concrete. I would say that in my experience, concrete, let's say corrosion sensors are borderline between when it's beneficial to do structural monitoring versus visual inspection. Because one of the characteristics of corrosion is that it might vary very widely in different locations. So you might be placing your sensor here and there's no corrosion, and 1 meter away you can have huge corrosion. So I think it's very dangerous to go only in the sensor direction when we are addressing corrosion. I really recommend to mix visual and maybe instrumental inspection for addressing corrosion.
¿Alguna pregunta más?
Thank you, Daniel. Very interesting presentation. I was wondering if you could monitor structural elements that are underwater, like deep columns, or can you do that?
Yeah, that's possible. For example, we've been monitoring piers in harbors or offshore platforms. So in particular, with some of the fiber optic technologies that I will show in the next presentation, that's really possible to go underwater. Even in seawater, it's indeed possible. So it's a good example of maybe making it more accessible and cheaper to get data compared to having divers or more expensive ROVs or other techniques for underwater inspection. By the way, offshore platforms are another example of lifetime extension. We've done quite a number of projects where platform was designed for use for 30 years. Still looks good after 30 years, but the regulators say, no, it's 30 years was the design lifetime, you have to abandon it. So monitoring and showing that, for example, the fatigue life is significantly lower than designed is a way to safely extend the lifetime of those offshore structures.
Jorge, ¿no tienes dudas? ¿Sí?
Problema de costos. Entonces, los ejemplos que diste, ¿verdad? Y esta regla del 0,5 al 3% del costo de la construcción. En el caso de los taludes.
Mm-hmm. Well, this is only a generic number. I think it's a fair question to ask how much it costs, so I wanted to put a number there. But, I mean, in the case of a slope, what's the cost of the slope? Yes, it's more difficult to identify. So it might be more appropriate to speak about a cost per meter or of slope or something like that. So in that case, maybe you can count on 10 euros per meter or something like that to monitor a long extension of, for example, the sinkhole project, the settlement example that I showed was in this order of magnitude, 10 euros per meter. That's about what it costs to implement a distributed monitoring system. So I maybe in the next, yes, lineal.
Metro lineal, ¿no?
Sí. That cost doesn't apply if you have only 2 meters, though. That's typical of customer. They ask a quote for 10 kilometers. They say, oh, let's start with 10 meters.